Have you ever wondered how scientists can tell what elements make up a star millions of light years away? This seemingly magical ability is made possible by something called spectroscopy. In its most basic definition, spectroscopy is a scientific technique used for determining the composition of substances. Think of it like a mystery novel, where the detective is trying to identify the culprit. But instead of a suspect, we're dealing with chemicals, elements, and compounds. And our detective tool is light. There are different types of spectroscopy, each with its own unique way of unraveling the mysteries of matter. Some types include absorption spectroscopy, fluorescence spectroscopy, and Raman spectroscopy, just to name a few. Each type can tell us something different about a substance, like its structure, concentration, and even its temperature. One such technique that has made significant contributions to various scientific fields is atomic emission spectroscopy, our focus today. So, what is the principle behind atomic emission spectroscopy? To understand this, it's important to know that this technique is all about measuring the electromagnetic radiation emitted by atoms. Imagine a bustling city at night. Each neon sign, each streetlight, each lit window, they all emit a different color of light, creating a unique skyline. Similarly, every atom emits a specific wavelength of light when it's excited, and this is what we measure in atomic emission spectroscopy. Let's delve a little deeper. When an atom is excited, either through heat or electricity, it's like it's been given a jolt of energy. This causes the electrons in the atom to jump from a lower energy level to a higher one. But electrons prefer to be in a state of lower energy, so they quickly fall back down. And when they do, they release that extra energy they had in the form of light. This light, or electromagnetic radiation, is what we measure. Now, each element has a unique atomic structure with a different number of electrons. And these electrons occupy distinct energy levels. So when these electrons get excited and subsequently relax, they emit light at specific wavelengths. This gives each element a unique atomic emission spectrum, much like a fingerprint. For instance, if we excite a sample of hydrogen, the light it emits will be different from that of helium. By passing this emitted light through a spectrometer, we can separate it into its individual wavelengths. This creates a spectrum, a kind of barcode, unique to each element. In essence, atomic emission spectroscopy allows us to identify an element by its light, by its unique spectrum. It's like identifying a city by its skyline or a person by their fingerprints. And it's not just about identifying elements. The intensity of the emitted light can tell us how much of an element is present in a sample. So, in a way, we can also quantify elements. This uniqueness forms the basis of identifying and quantifying elements in a sample. And that, in a nutshell, is the principle of atomic emission spectroscopy. So how do we go from understanding the principle to actually using it in practice? The answer lies within the instrumentation of atomic emission spectroscopy. These key instruments, which include the energy source, sample holder, monochromator, and detector, work in unison to create and measure atomic emission spectra. Let's start with the energy source. In atomic emission spectroscopy, the energy source is crucial as it excites the atoms and causes them to emit light. This energy source could be a flame, an electric arc, or a plasma source, depending on the particular setup. Now, once we have our energy source, we need to introduce our sample. This is where the sample holder comes into play. It's designed to hold the sample in the path of the energy source, allowing the atoms to absorb its energy and subsequently emit light. But how do we isolate and measure this emitted light? That's the job of the monochromator. The monochromator is a device that disperses the light emitted by the excited atoms into its component wavelengths, much like a prism dispersing sunlight into a rainbow. By doing so, it allows us to focus on a specific wavelength and ignore the rest. Finally, we have the detector. The detector's role is to measure the intensity of the light at each wavelength. It converts the light energy into an electrical signal that can be processed and interpreted. The intensity of this signal at any given wavelength corresponds to the amount of light emitted by the atoms, which in turn can be used to determine the concentration of a particular element in the sample. So there you have it. From the energy source that excites the atoms to the sample holder that positions the sample, the monochromator that isolates the emitted light, and the detector that measures this light, each instrument plays a vital role in atomic emission spectroscopy. With these instruments, scientists can accurately detect and measure the presence of different elements. So, where can we see atomic emission spectroscopy in action? Well, this powerful tool has found its place in a diverse range of fields, from environmental science to medicine and even astrophysics. Let's dive into some of its key applications. First up, we have environmental science, where atomic emission spectroscopy plays a pivotal role in pollution monitoring. It's all about the analysis of trace elements in environmental samples. Think about it, our environment is constantly bombarded with various chemicals and pollutants, and it's crucial to identify and quantify these to maintain the health of our ecosystem. Atomic emission spectroscopy allows scientists to detect and measure these pollutants, even when present in extremely low concentrations. Whether it's air, water, or soil, this technique provides a detailed snapshot of the elemental composition, helping researchers track pollution sources, monitor changes over time, and develop strategies to mitigate environmental damage. Next, let's talk about its application in the medical field, specifically in trace element analysis. Our bodies require a delicate balance of various elements, and any imbalance can lead to health issues. Atomic emission spectroscopy is used in clinical labs to analyze biological samples, such as blood or urine, for the presence of these trace elements. This can help diagnose a range of conditions, from mineral deficiencies to heavy metal poisoning. It's a non-invasive, accurate, and efficient way to get a glimpse into our body's elemental makeup and ensure everything is in check. Lastly, we journey to the stars, where atomic emission spectroscopy plays a crucial part in astrophysics, especially in analyzing the composition of stars. You see, each element, when heated to a high temperature, emits light at a specific wavelength. By observing this light or emission spectrum, astrophysicists can determine which elements are present in a star. This knowledge is key to understanding the life cycle of stars, the formation of galaxies, and ultimately, the origins and evolution of our universe. But these are just a sampling of the myriad of applications of atomic emission spectroscopy. It's also extensively used in industries like metallurgy, forensics, geology, and even archaeology. From monitoring pollution levels to diagnosing health conditions, from studying the stars to solving crimes, this versatile technique has made significant contributions across various fields. In essence, atomic emission spectroscopy is not just about identifying and quantifying elements. It's about understanding our world at its most fundamental level, from the soil we walk on to the stars we gaze at. It's a powerful tool that continues to push the boundaries of our knowledge, helping us uncover the mysteries of our universe one atom at a time. These applications are just a few examples of how atomic emission spectroscopy contributes to our understanding of the world. So to summarize what we've learned today about atomic emission spectroscopy, we started off by exploring the fundamental principle that underpins this technique. Atomic emission spectroscopy, or AES, is based on the concept that atoms, when excited by high energy, emit radiation that corresponds to specific wavelengths. This emitted radiation forms a unique spectrum, a fingerprint if you will, that can be used to identify and quantify the atomic composition of a sample. From there, we delved into the world of instrumentation. The heart of an AES system is its energy source, which is usually a flame or a plasma. This source excites the atoms in the sample, causing them to emit their characteristic radiation. The emitted light is then isolated and quantified using a spectrometer, a device that splits the light into its individual wavelengths. The intensity of each wavelength corresponds to the concentration of the element in the sample. But what really brings the power of AES to life are its applications. We discussed how this technique is used in a wide range of fields, from material science to environmental monitoring, and from forensic science to the food and beverage industry. AES allows for the detection and quantification of trace elements, even those in very low concentrations, making it an invaluable tool for those seeking to understand the composition of materials or the nature of environmental contaminants. Through all these discussions, we've seen how AES combines the laws of physics with cutting-edge instrumentation to provide us with a powerful tool for analysis and discovery. It's a testament to the ingenuity of scientists and researchers who continue to push the boundaries of what's possible, using tools such as AES to shine a light on the unknown. That's all for today's journey into the fascinating world of atomic emission spectroscopy. Subscribe for more because you won't find me later.